Good morning. We're going to start with the discussion of polarization in chapter 4. To do this, first let's recall what we have done so far. In whatever we have done to define electric field or potential, we have so far been dealing with point charges. So if I think a little more deeply about point charge, when I say a point charge, I mean to say there is a charge that is located at some specific point. But a point is an idealization. For example, when I write this electric field of this point charge plus Q as KQ by R square radiating out, then what do we mean by a point charge? What happens when R goes to 0? There is no such thing because no charge is point-like. Even an electron is not point-like. It has some extension because any charge is a property of a massive body. That's why it's important to have these definitions. And a massive body is a physical thing, and any physical thing has extension. That is, it has one part outside another. So when we mean a point charge, when we say a point charge, what we mean is it's an idealization, it's a mental construct. No charge in reality is point-like. It's just some mental construct that we're using, some physical aspects like extension of an object that we are intentionally turning off to learn more about what we can do with point charges and then extend it to other things. And that's what we have done so far in chapter 3. That is, we know that no charge is point-like. So in general, we have extended charge distributions, not point charges. But then in this extended charge distribution, I can break that mentally into tiny cells and go around each cell and integrate to find the potential or to find the electric field. And because no charge distribution or no charge is like point-like charge, because every charge distribution is extended, we were able to perform what we called as the multipole expansion. So in multipole expansion, that's exactly what we're doing. We're saying that, okay, if I have a charge distribution like this, the total charge of this charge distribution is, let's say, Q. And this total charge Q itself doesn't depend upon the geometry really. We're just counting all the charge that is in the body. And that gives us the first term we called the monopole term in the multipole expansion. And the next term is looking at how these different charges are distributed with respect to the origin. That is, so one charge may be here, one charge may be there, and we can find out the geometry and we can incorporate more terms into this multipole expansion. That's what we have seen. We could include dipole, quadrupole, and so on and so forth. And we achieved that by looking at, for example, if I'm interested in field at point P, which is at a distance r, and the point that we're interested in is at a distance r prime, then what we essentially did was we took this r minus r prime and we performed a Taylor expansion on this one to figure out what were these monopole terms, dipole terms, and quadrupole terms. In fact, in the last lecture, in lecture number 21, we looked at in detail using separation of variables and using, in fact, a specific dipole. That is, we started with the problem of, this is also on homework number 6. So if you have two charges, right, and they're placed A above and A below, we used phi of z as a boundary condition, and then we were able to expand in spherical polar coordinates, and we were able to figure out what was phi L is equal to one term, and this term is what we had seen was the dipole term. So in fact, for a dipole like this that you're seeing here, we could write the potential phi of a dipole at r as r dot p by r square. Of course, there is k here. So this is how we were able to write it. So and this p was an integral that we saw was equal to r prime rho of r prime dv. That is the volume. So if I have some extended charge distribution like this, and I want to figure out what is the dipole moment of this part, then I use this integral to find out the dipole moment. And we got this definition from multipole expansion. So we have now the potential for a dipole. So how could we find the electric field from a dipole? That's very straightforward, right? Electric field is simply negative gradient of phi. So all that I need to do is negative gradient. I have k times negative gradient of r dot p by r square. This is the unit vector r. And this gradient, I can, for example, perform it in spherical polar coordinates. Right? If I do it in spherical coordinates, then I can get, using the gradient formalism in the formula for gradient in spherical polar coordinates, you can see that this comes out to be something like, for the r component for ER, you would get minus dou phi by dou r, right? So, or you get minus dou by dou r dot p by r square, or that gives you minus dou by dou r p times cosine theta by r square, if theta is the angle between r and p, and that you can write it as 2p cosine theta, this is just the magnitude, divided by r cube, right? I'm not writing k because k is just a constant, so I'm not writing it there. So you would get 2p cosine theta by r cube for the r component. Similarly, you can write what is the theta component, e theta. The e theta component would be minus 1 over r dou phi by dou theta. This is from the spherical polar coordinates once again. So then if I do that, minus 1 over r dou by dou theta, we had r dot p by r square, so that would give me minus 1 over r. You can see that this r square doesn't really depend upon theta, so I can pull that out and write it as r cube, and then write dou by dou theta p cosine theta. So this gives me dou by dou theta of p cosine theta simply gives me p times sine theta by r cube. And there is a negative sign that comes out, so this negative sign here becomes positive, right? And then there is no phi component here. There's no phi component because in r dot p, in this term r dot p, there is no phi. So E phi is equal to 0, or we can write the electric field of a dipole as ER along r plus E theta along theta plus E phi along phi, and this is 0. So, and this we have seen in the last term that it is 2p times cosine theta by r cube plus p sine theta by r cube, and of course this whole thing is multiplied by k, the constant. And here we can see that this p is common, right? And this is r and theta, so we can get this as k times p by r cube times 2 cosine theta r plus sine theta theta. So this would be the electric field from a dipole, and we got this from the multipole expansion, which we discussed in several lectures. I'm not going to go over it again here, but if you have any questions about the multipole expansion, I suggest that you go back to lecture 21. And in general, you will see this as a homework problem. So in general, we can write this Kp by r cube as k times k by r cube times 3 times p dot r minus p. This is very similar to the way we symmetrized the quadrupole moment. If you remember, we symmetrized the quadrupole moment in a particular way. So it's very similar to that. So how you go from here to here would be, problem 3.33. in the homework that you will see, the next homework 7, problem 3.33 in the textbook. Okay, so now we know how to understand dipoles. And whatever dipole that I'm drawing here is also an ideal dipole, because again, in the dipole, I'm considering that if I go by a distance A, I have a point charge here. And because point charge itself is an idealization, even this dipole is an idealization. So if we have this ideal dipole, we can talk more about it. Um, we can look at and see what happens if we place this dipole, say, in an electric field, right? So if I have a dipole, if I have some sort of a dipole that's like this, let's call this positive, and let's call this negative Q. We have two charges that are separated. Let's say they're separated by a distance d. Then if I place this dipole in an electric field, let's for now, for the moment, think that this is a uniform electric field, or even a non-uniform electric field. Let's say in general any electric field. So this is at x, right, and this is at x plus d, or in general we can write this d as delta x. If you write it as delta x, then I can write this as x plus delta x. So then the force on the positive charge is plus q times electric field at where the point charge is, x plus delta x. Similarly, force on the negative charge is minus q times electric field at its location x. We're just considering in general. It doesn't need to be a uniform field. That is, you don't need to have the same electric field here and here. So that's why we are writing this as E x plus delta x at positive charge and E of x at the negative charge. So if I want the total force, then I simply need to add F plus F minus. We're calculating the total force on the dipole. So then that would give me QE of x plus delta x minus QE of x, or I can write it as Q times E of x plus delta x minus E of x. Now, if I multiply and divide by delta x, if I look at this Q times delta x, and then I have this factor, E at x plus delta x minus E of x divided by delta x. So this Q times delta x is what we defined as the dipole moment. Right? The dipole moment that we defined was, P is equal to the integral of r prime rho of r prime times dv. Right? In this case, you just have two charges, right? Two charges that are located at x and x plus delta x. And so if you actually do this, you would find out that the dipole moment is nothing but q times delta x. In this case, if the charges are separated by an amount delta x, right? Then if I take this in the limit of delta x goes to 0, then I have q times delta x as p. And look at this. This is simply a derivative, because you're taking the value of the electric field at x plus delta x, subtracting what it was at x, and dividing by delta x. So it is sort of the slope, the tangent, the slope of the tangent. So this is simply dou E by dou x. So the total force then is P dou E by dou x. But what if we have not just electric field along the x-axis? What if we have electric field in 3 dimensions along x, y, and z? Then you would get the same thing along x, y, and z. And you also notice that this dipole moment P, we wrote it as Q delta x. So this is really Px. That is, they're separated by delta x along the x-axis. So in 3 dimensions, they could be separated by delta r, which means their separation along x, y, and z need not be the same. So you could have for the same physical situation, you could have Px, Py, Pz, which would be Q delta Y, Q delta Z, so on and so forth. Because the component of the distance between these two charges, if I have in general in 3 dimensions, if I have some charges like this, right? If this is delta R, then I can break the delta R into delta X, delta Y, and delta Z, and have a dipole moment along X, Y, and Z axis. And these dipoles would feel the force from the gradient of the field. So in a uniform field, there is no net force on a dipole. Why? Because if the field is uniform, this would be plus QE and this would be minus QE, so they would just cancel out. If the field is same at X and X plus delta X, so there would be no net force on a dipole if you are in a uniform electric field. On the other hand, if you are in a non-uniform electric field, for example along the x-axis, then you can see that the force is dE by dx. So then we can write in general the total force in all the 3 dimensions as I have Px along x-axis and Py along the y-axis and Pz along the z-axis. Or in general, I can write this as Pxi plus Pyj plus Pzk dot dou Ex by dou Xi plus dou Ey by dou Yj plus dou Ez by dou Zk. Right? Or in other words, I have this as the total dipole moment vector P dot, if you look at this, you can express this as the gradient of E, right? That would be the gradient of E, right? And then that way we would see that this is nothing but P dot gradient of E. So that would be the total force on a dipole in an electric field. And so if the electric field is uniform, then the dipole would feel no force because this term would be 0 if the field is uniform. Now, what about the torque? So what about the torque? So if we want to find out torque on a dipole, right, we know that torque is equal to R cross F. So if we take a dipole and some electric field, right, now let's say the dipole is like this, at plus Q and minus Q, let's say they are separated by delta X and they're at an angle theta to the electric field E. Then if I take the center point, if I'm looking from the center point, plus Q is delta X by 2 to the right and the negative one is minus delta X by 2, or it is to the left. Right. So then I can write the torque on the entire thing as R plus cross F plus R minus cross F minus, and so then these things would be equal to, we can write it as delta X by 2. We can write it as R plus as delta X by 2 like shown in the figure cross Q times E, where Q is the charge, plus here I have minus delta X by 2 because it is to the left for the negative charge. So I have minus delta X by 2 cross minus QE. So then this minus and minus essentially give us a plus, so we would have 2 times delta X by 2 cross Q times E, or we can write it as Q delta X cross E. Don't forget that this delta X is a vector, so this is a dipole moment vector, so P cross E. So the torque on the dipole is equal to P cross E. So we can also calculate the potential energy very easily from here. In fact, if you were to think about what is the energy needed to go from, say, theta is equal to 0 to a particular angle theta is equal to theta naught, then you can use mechanics, for example, the potential energy for this theta 0 would simply be going from 0 to theta 0 torque times d theta, right? So that would be given as the magnitude itself of torque is PE, and this would be PE sine theta, right? The cross product gives sine theta here, so we'd have sine theta d theta going from 0 to theta naught, so that this would be equal to PE times 1 minus cosine theta 0 if you perform the integration, right? So then now let's talk about dipole moments of atoms and molecules. So far what we have done is just like how we have ideal point charge, and we described an ideal point charge, and from there we were able to make much progress to calculate electric field for any extended charge distribution. In a very similar way, what we did now is instead of a monopole, the point charge, we are looking at a dipole. So we are looking at two charges that are separated from each other, and we're looking at this ideal dipole, because even within this dipole we're still considering the charges to be point-like. So this is an ideal dipole, and using this, now our ultimate aim is to describe what we see in reality, describe the physical things that we see in reality. And so equipped with this knowledge, we're going to discuss dipole moments of atoms and molecules. To do that, let's start considering the hydrogen atom. And here we have to pause a bit in discussing electrostatics, and we need to discuss a little bit of quantum to truly understand what we mean by this dipole moment in an atom. So in an atom, it's not the electron doesn't go around the proton like how Earth moves around the sun, right? Because quantum mechanics describes how atoms behave and how electrons behave in an atom. For example, hydrogen atom. If you are taking a quantum mechanics course, then you would calculate the wave function for electrons. If you have not yet taken it, then in the future, if you do, you will see how you calculate the wave function of the electron. Quantum mechanics is a statistical theory. That means we really are describing the statistical nature of electrons, not really single particles. So quantum mechanics does not describe single particles. And so when we look at this so-called entity called the wave function in quantum mechanics, this wave function tells us statistical probability of finding an electron at a given location. So in an atom, really, you have a nucleus at the center, but the electrons are not going around in a circle. They're really like a charge distribution around. That is, this wave function, the psi squared, the wave function squared, that gives you the probability. So in an atom, essentially what you have is at the center you have a nucleus, and around it you have a probability cloud. It is not a single particle going around like Earth going around the sun. Rather, what we can describe rather is this probability cloud around it. And so when you apply an electric field, you're changing this wave function, and you're changing the energy of this electron, and you're changing the way this electron probability is distributed around the nucleus. And that's how you get a dipole moment. So coming back to now electrostatics, so imagine you have a nucleus, and you have, I'm going to draw this electron cloud in another color here. So this green is electron cloud. This is in 3D. I'm just drawing a cross section. So the electron cloud is not going through the nucleus. The nucleus is at the center, at a certain distance, or outside this nucleus there is a spherical cloud of this probability distribution that is surrounding the nucleus. So when we apply electric field, it is this charge distribution that we are perturbing. It is this probability cloud that we are perturbing. So we can see what would be the electric field inside the atom, what would be the intrinsic or internal electric field that comes within a hydrogen atom, which is very simple to calculate, right? So that is from, for example, if you consider the classical model, right, that the electron is at, let's say, a distance a from the nucleus, then the electric field of that electron would be simply 1 by 4 pi epsilon naught E by A square, right? So then that would be equal to roughly 9 into 10 to the power 9, that's for 1 by 4 pi epsilon naught, and divided by the radius of an atom is roughly 1 angstrom, or that's roughly 10 to the power minus 10 meters. So this would give us 10 to the power minus 20, and the charge on electron is 1.6 into 10 to the power minus 19 coulombs, and the net electric field is in volts per meter. So if you do the math, you would have around, you have minus 20, minus 19, and 9 into 1.6. So you roughly get something like 1.4 into 10 to the power 11 volts per meter. So this is the strength of the electric field that is inside the atom, 10 to the power 11 volts per meter. This is a very high field. So any field that we apply externally, which is much smaller, I'm talking about the usual application. So if you were to put an atom across a capacitor that is powered by, let's say, a battery, right? How much electric field could you generate? And if you look at those electric fields, those external electric fields are much smaller, right? And so this electric field is much higher. So you perturb the distribution, the probability distribution, or the electron cloud very little. So in actuality, we may have just a little bit of change. So this charge distribution may be a little elongated. Of course, I'm drawing an exaggerated version, but once you apply an electric field, the electron cloud is a little elliptical, not spherical really, because of the external electric field. But this is going to be very little. In fact, we can say, if I applied, say, the external field is E external, then if I compare that to E internal, let's say the charge cloud got displaced by an amount delta x because of the application of the electric field. So the effect of the external electric field is on the order of delta x, whereas the effect of the internal field is over a radius of A, right? And so this gives us roughly what we can see as a linear approximation to a curve. That means that if you double E external, right, the difference in the position of the charge centers, that is the charge center of the positive charge nucleus and the charge center of the negative charge, they move a little bit, and that the difference between those charge clouds is given by delta x. So now we know that E internal is like A squared, because it goes as 1 over A squared. So then from here we can see that we saw that E external by E internal goes like delta x by A, because that's the length scales where they're operating. But on the left hand side, E external by E internal goes as 1 over 4 pi epsilon naught E by A square, right? So this is delta x times A. And so if you were to look at it from this way, if you look at this, then E external 1 by 4 pi epsilon naught times E by times delta x by A square times A. I just moved this factor up to here. And we can define this E times delta x as the polarization P, right? So if you apply an external field, then the charge centers are separated from each other, which causes the dipole moment. That's this E dx. And so I can write that as P by 4 pi epsilon naught A square times A is A cube. Or we can from here see that the dipole moment is going as E external times some quantity, 4 pi epsilon naught A cube. Now this, as you can clearly see, A was the radius of the atom that we had taken, the distance between the nucleus and the electron, and so this is a constant in a way. that is for this atom, for hydrogen atom, because A is fixed. In general, we can look at this as polarizability term, which is defined by alpha. We call this alpha as polarizability. And this is the applied external field, which is also a vector, right? So in other words, what we are saying is that if I have a neutral atom, that is, if I have a positive charge at the center and an electron cloud. So when we say an electron cloud, the center of this electron cloud, we're talking about the center of this electron cloud and the center of the positive charge. We're talking about the distance between those two. So without electric field, the electron cloud is spherically symmetric in the hydrogen atom, and upon application of external electric field, the charge centers, the negative charge center, it's elongated, so the negative charge center and the positive charge center are separated by an amount of delta x, and that's why we say this has a dipole moment of E delta x, that is the separation between the positive and negative charge centers. And what we are saying is that this dipole moment that is induced is effectively caused by this E external. Because E external has been switched on, that's how you got this delta x. So this P, whatever it is, depends upon the external field, and that dependence can be expressed using this, like we have seen, and where we call this alpha as polarizability. Now here P is a vector and E is also a vector, so alpha is not really a scalar, it's not a constant in the sense of a scalar, that is, it's not just a number, because it depends, in which direction you are applying the external electric field. Because depending on the direction, for example, if you take a material, right, if you take a material like silicon oxide, for example, it depends which direction you are applying, or carbon dioxide, even much simpler. It depends upon which. So if I have CO2, it depends upon whether I apply the electric field this way or whether I apply the electric field this way. So the polarizability in this direction would be different from the polarizability in this direction. So this polarizability is really what we call as a tensor. It's connecting two vectors. So this P is, you could think of it as Px, Py, Pz, right? And similarly, E external you could think of as E external x, E external y, and E external z. And to connect these two, we have a 3x3 matrix, right, which is alpha xx, alpha xy, alpha xz, alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz. So this is the polarizability tensor. So now let's take a look at molecules. We have just spoken about atoms right now. We spoke about how the center of the electron cloud, we are calling it a cloud because quantum mechanically speaking, we cannot talk about a single particle really, because quantum mechanics doesn't describe a single particle. So what we have rather is an electron probability distribution cloud. The center of this negative charge distribution cloud moves away from the positive charge by very little when you apply an external electric field, and the dipole moment that is induced by the application of external electric field could be written as P is equal to alpha E. This is for atoms, and this alpha is a polarizability tensor. So now if we look at molecules, we could sort of subdivide these molecules into two different parts. One is polar and another is non-polar. So a typical example for a polar molecule is something like water. So you have a permanent dipole moment in a molecule like water because you have a big oxygen atom and two small hydrogen atoms, and this oxygen atom is pulling electrons away from the hydrogen atom. So you have a slightly plus charge here, and then you have a slightly negative, you have a slightly negative charge here and slightly positive charge here. And so water has permanent dipole moment, right? And non-polar molecules, for example, if you were to take something like kerosene, it's a non-polar molecule because it's a hydrocarbon, right? And it only consists of length chains of carbon and hydrogen. So it would look something like carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, and it extends out, and then you just have basically more of this repeating. So there is no permanent dipole in this molecule, and that's why we call it as a non-polar molecule. And an interesting thing is that if a molecule has a permanent dipole moment, then it so happens that that permanent dipole moment creates certain energy states in the molecule that absorb infrared radiation very effectively. So wherever there is a permanent dipole moment like this, like in water, you would absorb a lot of IR. In fact, we have these ND YAG lasers in the lab. These are pulse lasers that produce laser pulses at 1064 nanometers, for example, with a pulse width of 7 nanoseconds. We use it to do a lot of different experiments. But sometimes we want to, instead of 1064, we have a process where we can convert this into 532. But there is still some 1064 left, so we need to absorb it. So what we do is, if we have a laser and the laser beam is coming out of the laser, we place a water column, and when it goes through the water column, whatever 1064 is, that's infrared radiation, it is absorbed by the water column. And this happens because water has a permanent dipole moment in it. Another interesting thing about this is, now if you look at carbon dioxide, you would think that there is no you would think that there is no dipole moment in carbon dioxide, but as you can clearly see, with two oxygens on both ends, you have a lot of scope for dipole moment here, because oxygen is highly electronegative, and so oxygen pulls the electron. So this absorbs a lot of infrared, and that's what leads to global warming, because if the carbon dioxide, because of its dipole moment, it absorbs infrared radiation, and if we keep producing more and more CO2, then that absorbs more and more radiation, and then as an effect, you have what I call as car in the parking lot effect. This is a better way than a greenhouse effect, because if you have ever parked a car outside without leaving the windows in on a summer day, and then you went back to car, as soon as you open the car door and get in, you can feel that it's very hot, right? So that's what happens. So producing more CO2 and putting more CO2 out basically leads to more absorption of the infrared radiation due to the dipole moment that is inside the carbon dioxide molecule, leading to global warming. And what we will see in the next semester is, how does a dipole emit radiation, or how does a dipole absorb radiation. We will talk about that in the next semester, because that requires dynamics, the motion of the dipole itself. And in this semester, we're not going to be able to focus on dynamic effects, so we're pretty much covering only static effects. So now that we know that there are polar and non-polar molecules, now we can look at materials that are made of these atoms or molecules. So if I have a slab of some material, let's say, right, I cut out a small slab from some material, and then if I place it in an electric field, then all the molecules and all the atoms are polarized by the effect that we described, depending upon what they are. If it is hydrogen, it is polarized accordingly. CO2 is polarized according to its structure and its nature. So what we would end up having is we could think of these these elongated charge clouds in these materials around wherever there is a nucleus. So around that nucleus it is extended, and we have positive charge and negative charge, right? Positive charge and negative charge. So we have these tiny dipoles that are extended out in the material. So these are the same dipoles that are extended out. But if you draw a line between the top and the bottom, all the dipoles in would just cancel out, because this negative charge would cancel out this positive charge. This negative charge would cancel out this positive charge. So in effect, we can treat a polarized material as if it's all the charge is on the top or all the charge is on the bottom. And in between, the polarization is 0, because they effectively cancel out. The negative charge from a molecule that's higher cancels the positive charge from a molecule that is below, right? And we can also see what would be the polarization here, right? So if we take the net polarization dP, small polarization p, to be p times dV, that is, if I were to take a small volume within this material, small volume dV, I'm counting how many dipoles are within that volume and multiplying it. So let me rewrite it. So we have dP is equal to p dV, right? So now if I take a small area here, let's call this dA, and let's say this is the z-axis. So I'm taking a small area dA on the top surface, and let's say this is positive and this is negative. So we have, let's say this has, let's extend this into a cylinder with dz. Then we can write dP as p times dA is the area times dz, right? So then we can say that the effective dipole moment of a segment of length dz, so the effective dipole moment of a segment of length dz is p times dA. Or we can write the total charge that is separated out here is p times dA, that is the surface charge, times you integrate it over the entire surface, so you essentially get p times A. Right? So the total charge is p times A, where p is the total polarization of the material. Or in other words, what we are saying is that if you take a slab of some material and you apply electric field, then you end up creating these dipoles, but dipoles within this cancel out, making it look like there is a net charge plus sigma and a net charge minus sigma on the top and bottom, and this total charge is equal to the net polarization. That's what we are essentially saying here, right? So then we can consider this slab as a parallel plate capacitor with plus P on the top, plus P charge density on the top, and minus P charge density on the bottom. Then we know that if you have a plate with sigma, we know that the electric field coming from that is sigma by 2 epsilon naught n, pointing this way. So we can apply the same thing here, but inside here you would have 2 times sigma by 2 epsilon naught, or you would have sigma by epsilon naught, and that becomes p by epsilon naught, because the charge is p. Or we can write the electric field as 4 pi times kp. 4 pi times k is 1 by 4 pi epsilon naught times 4 pi, so it gives you 1 by epsilon naught, which is what you have here. So you can write the electric field inside this polarized material as 4 pi kp. This is just a constant, so the electric field inside is proportional, or goes like the total dipole moment induced. And in fact, we have seen in case of conductors
that this net field that is inside becomes zero, because these dipoles would produce a field that counteracts the applied electric field, so that the net inside field, the total field, that is the field generated by the dipoles plus the external field, together give the total field to be zero inside a conductor, right? So here we will stop here with the discussion of polarized materials, and in the next lecture we will consider more geometries, and we will discuss the dielectric constant, and we will also try to discuss surface plasmon resonance in a little detail. Thank you.